Good day, students. Welcome to part 1 on the trapezoidal rule. We're going to be using the trapezoidal approximation to estimate the area under a curve. Okay, so let's start off by writing down the formula. The area underneath a function, let's call it f of x, from, let's say from x of 1 all the way to x of n can be approximated by, so the area, the expression for the exact area basically is the integral, the definite integral from x of 1 to x of n of f of x dx. Now this can be approximated using something known as a trapezoidal approximation or trapezoidal rule. So in this case, we're going to use the trapezoidal rule with n equal subintervals. Okay? And the trapezoidal rule can be given by w over 2, the textbooks use h, times f of x sub 1 plus 2 f of x sub 2 plus, the pattern goes on, plus 2 f of x sub n minus 1 plus f of x sub n. Okay? Now if you notice, both endpoints are included, and every endpoint, every calibration in between the endpoints, when you input it into the function, you also have to double it. Okay, so everything in the center, the heights in the center are doubled, but the first and the last height are not doubled. Well, why is that the case? How is that possible? Well, we're going to derive the trapezoidal rule in two different ways to help you see why this formula is the way it is, okay? Now let's take a look at this curve right here. Let's use n equals 3, okay? Let's say this is x. This is x of 1 right here. Let's call this x of 1. x2, x3, x4. As you can see, the way I partitioned my interval x1 to x4, I have 3 sub-intervals of equal width. Okay, so from here to here is w, and w is equal to 3. Okay, the same goes for all the other sub-intervals that I have. Okay, so that's w, and that's w. They're all equal to 3. Okay? Now, what if I want to approximate the area from x1 to x4 using trapezoids, or the trapezoidal rule? Well, this is how it's going to look like. We're going to make 3 rectangles. So let's do this in blue. All right, so there goes my first rectangle. All I do is I'll just trace my calibration. My calibration is all the way to the curve, and then I'll connect them in this nature. So there goes the first trapezoid. Second trapezoid, just trace this to the curve, and then connect this dot like that. That goes my second trapezoid. And then my third trapezoid, just trace that calibration up to the curve, and then connect it from here all the way to there. Okay? So as you can see here, we have 3 trapezoids. Let's call them T1, T2, and T3. Okay? Now, before we can derive the trapezoid rule, here we are going to recollect our formula from geometry for the area of a trapezoid. Okay? So let's recollect that real quick. Area of a trapezoid from geometry is basically 1/2. We can 1/2 times the sum of the parallel sides, base 1 plus base 2 times the height. Okay? If we apply it to this situation that we're dealing with here with a function, it's going to look like this. The width over 2 times f of x1 plus f of x2. Okay, so that's this formula adapted to this situation we're dealing with right here. Okay, so let's go ahead and let me indicate where f of x1 is. So if you trace this to your y, this will be f of x1, and then if you trace this point right here, somewhere around here will be f of x2, and then if you trace that point out, it's not perfectly straight, somewhere around there will be f of x3, and then the highest point up here, trace it out, that will be f of x4. Okay, so these are the bases, but since our trapezoid in this case is standing on its height, so they are basically, our bases are kind of like the heights, and our height for the formula is kind of like the width. Okay, so this is base 1, base 2, height, base 1, base 2, height, base 1, base 2, height. In this case, we're using f of x1, f of x2, width, f of x2, f of x3, width. Okay, all right, so using that, let's find the area of our individual trapezoids. Okay, so area of trapezoid 1 is equal to um, 1/2 times base 1. Base 1 is f of x1. This is base 1 right here. Plus base 2, which is f of x2, times the height, which is w. Okay, I want to write it in the formula that you're familiar with before I derive this final formula. Okay, all right, and then the area of trapezoid 2. Can you tell what the area of trapezoid 2 is going to be? It's 1/2 times, what is the base 1 for trapezoid 2 is the same thing as base 2 for trapezoid 1, which is f of x2 plus the second base for trapezoid 2 is f of x3, and the height is w, same as f of x1. Okay, and then area of trapezoid 3, can you tell what that is? It's going to be 1/2 times f of, where we stopped in the other one, f of x3 plus f of x4 times the height, which is w. Now you see what's happening here? You see that the interior bases or heights are repeated. Okay, you see it occurs once in trapezoid 1 and then trapezoid 2 here for f of x2, and then f of x3 occurs in 2 and 3. That's why we have the 2's here. Okay, so let me combine all these formulas for you. So the total area is going to be area of T1 plus area of T2 plus area of T3, right? So what is that going to look like? We're going to have 1/2 times, we can bring the w to the front, so let's write it as w over 2 times f of x1 plus f of x2. That's the first one, plus w over 2 times f of x2 plus f of x3 plus w over 2 times f of x3 plus f of x4. Fit that in there. Okay? All right, now let's simplify this, and then we're going to see how this formula comes about. If I simplify this, I'm going to end up with the following. I'll have the area in this situation is going to be, I can factor out w over 2 from all of them, factor out w over 2, and what do we have next? You notice that f of x1 is just by itself, f of x1, plus, now f of x2 shows up twice in trapezoid 1 and trapezoid 2. So that's why the interior heights are doubled because of that situation. So you have times 2 f of x2 plus, and if you look at trapezoid 2 and 3, these two repeat itself. So that's why those ones are doubled also. So 2 times f of x3, and then the endpoints are not doubled because it shows up once in each trapezoid, so f of x4. So this is the trapezoidal approximation of the area under this function. Okay, so if I extrapolate this solution right here, we can see why this formula is the case. Okay, all right. Now there is another way that we can come up with exactly the same formula. Okay, I derived this using geometry. Now we can also derive the same formula by using two approximation methods that we learned before. These are the left endpoint and the right endpoint rectangular approximation. Okay, so how is that possible? Well, let's see if we can do that here. Now, what if I wanted to do, for this same problem, what if I wanted to do the left rectangular approximation for for three subintervals. So that one is going to be the left rectangular approximation, W over 2, and then we're going to skip the right endpoint. So it's going to be times f of x1 plus f of x2 plus f of x3. Okay? I covered this in a previous tutorial, so you can review that if you've forgotten. How about if we wanted to do a right rectangular approximation using three subintervals? W over 2 equal with, now we're going to skip the left endpoint and we'll start from f of x2 plus f of x3 plus f of x4. Now what happens if I add these two rectangular approximations? What do I get? LRAM plus RRAM is going to be equal to, you notice they both have W over 2 in common, so I can factor that out. So we have W over 2 oh, I made a mistake. For the rectangular approximations, there's no denominator, so let's erase that. Sorry about that. So there's no W over 2, just straight W. So let's fix that. So we have W, it's just a width, right? W. Okay, good. So since we have W common in the rectangular approximations, we can factor them out. So we take out the W times f of x1 is by itself, so we just have f of x1 plus, you notice f of x2 shows up here and here, so if I combine those two, I'll have times 2 f of x2 plus f of x3 shows up twice, here and here. If I add them up, I'll have plus 2 f of x3, and then f of x4 is just by itself, f of x4. All right? So what can we do to make this formula the same as that? We just simply divide it by 2, right? So just the average. So if I take LRAM and RRAM, add them together and divide by 2, it's just equivalent to dividing this by 2, and this is equal to your trapezoidal approximation, okay, using three subintervals. So these are two ways you can derive the formula for the trapezoidal rule, okay? All right, now that we have the formula down, let's go ahead and apply it to an example. All right, so for example 1, we're to use the trapezoid rule with 4 equal subintervals to estimate the area under the given function. And then we're to use the concavity of the curve to determine if this is an upper or lower estimate. And then we're to find the exact area and determine the percentage error. Okay, so for number 1, we are going to be considering the integral, the definite integral from -3 to 1 of the function negative x squared minus 2x plus 9 dx. Okay? So this is what we're going to be approximating using the trapezoidal rule. All right, so before I start putting stuff into the formula, I want to draw my interval and determine the width of my subintervals, okay? So 3, 2, 1, 0, 1. All right, so let's break it down and see what this looks like. So this is -3, -2, -1, 0, and then 1. Okay? Alright, so with this, this is x1, x2, x3, x4, and x5. What is the width of my interval right here? You can see that the width is all, they're all 1, right? So w is equal to 1. That's the width of my subintervals. Alright, so let's go ahead and plug it into the formula. And you remember another way to find the width is also by doing the length of the interval, which is 1 minus -3, divided by the number of subintervals you have, which is 4. And we can clearly see that this is 4 over 4, which equals 1. Okay? All right, so in this case, the trapezoidal approximation using 4 subintervals is going to be given by the width over 2. I'm going to write down the formula first, okay, and then apply it momentarily. W over 2 times f of x1 plus 2. You double everything in the interior, so all these x2, 3, and 4 will be doubled, and then x5 will stay alone, okay? So f of x2 plus 2, f of x3 plus 2, f of x4, and then the right endpoint will not be doubled, f of x5. Alright, so that's what we're going to be computing. Alright, let's apply this formula to this situation that we have. If we do so, what is our trapezoidal approximation going to look like? It's going to look like 1 over 2 times f of x1, what is x1? -3, plus 2 f of x2, which is -2, plus 2 f of x3, which is -1, plus 2 f of x4, which is 0, plus f of x5, which is 1. Okay, so please do not double the endpoints or else you're going to get it wrong. Alright, so that's that. Now let's calculate what our output values are. We'll just simply plug in these values into our function, okay? Don't forget, f of x is the integrand. F of x is -x squared. Let's do that again. -x squared minus 2x plus 9. Okay? Alright, so what is f of -3? Just plug in -3 here. We'll have -9 plus 6 plus 9, which is equal to 6. If we do f of -2, f of -2 is going to be, plug it into this function, -4 plus 4 plus 9, which equals 9. F of -1 is equal to -1 plus 2 plus 9, which equals 10. F of 0, it's easy, these two become 0, so it's just 0 plus 9, which equals 9. And then f of 1, the last one, is going to be -1 minus 2 plus 9, which equals 6. Okay, so we just plug in all these values into our formula right here, and that will give us a trapezoidal approximation. Alright, so let's go ahead and do that. So T4 is equal to 1/2 times 6 plus 2 times 9 plus 2 times 10 plus 2 times 9 plus 6. If you do the calculations, you have 68 over 2, which equals 34. Okay, so that's that. Alright, now we're going to use the concavity test. Is this curve concave up or down? It's pretty easy to tell. If you look at this function, if you differentiate it twice, your answer is going to be -2, right? So the square x dx square of our function, -x squared minus 2x plus 9. If you differentiate this twice, your final answer is going to be -2. So what does that tell you? It's negative, so it's going to be concave down. Okay, so it's concave down. You don't even have to use calculus to determine the concavity. If you see the negative here, you know that this is a parabola which opens up, but this minus means it's going to be opening, it's going to be reflected downwards, which opens down. Okay, so if our parabola opens down, what do you think? Where do you think our trapezoid is going to be located? Since it opens down, our trapezoid is going to be inside the parabola, right? So this means that our this is going to be a underestimate. It's going to be an underestimate, okay? So this is an underestimate or lower estimate. So underestimate is going to be, it should be less than the actual area, okay? All right, let's see, is this going to be correct? Let's see, we can only determine this by calculating the actual area, all right? So don't forget, if it's concave down, you have an underestimate on that interval, and if it's concave up, you're going to have an overestimate because the trapezoids are going to be outside, they're going to be above the curve, okay? So if you have a parabola like this, concave up, and you're drawing your trapezoids are going to be outside, which is an overestimate, just like we did in the previous derivation that I showed you with that function. Okay? All right, now let's find the exact area using FTC part 2. We're looking for the definite integral from negative 3 to 1 of negative x squared minus 2x plus 9. And we know what the power rule is for integration. If we integrate x to the n, it's x to the n plus 1 over n plus 1. So that's what we are going to be applying here. So if you do the term-by-term integration, if you integrate this first term right here, you have negative x to the third over 3. You just add 1 to that power, and then you make that the denominator minus 2. Now this has a 1, so it becomes negative 2x squared over 2. Okay? And these two 2's can divide out. And then this has x to the 0, so it's simply going to be plus 9x. Alright, so this is the antiderivative of this polynomial right here. We're going to be evaluating it from negative 3 all the way to 1. Okay, so using FTC part 2, we're just simply going to input this 1, the upper limit of integration, into the function, negative 1 to the third, evaluating the antiderivative of the upper limit, 1 squared over 2. Oops, sorry, 2 is gone already, so just 1 squared. Plus 9 times 1, okay? And then minus what? You plug in negative 3, so you have negative, okay, we can just make, if we do the calculations, negative 3 to the third is 27. Negative 27 times this is just positive 27 over 3, which is 9, minus 3 squared is 9. So minus 9, and then plus 9 right here. And actually 27, because 3 times 9 is 27. Let me just show you the steps. 9 times negative 3. Okay? Alright, so that's how you have it. FTC part 2, you plug in the 1 here, and then you plug in the lower limit, and then you basically subtract the 2 from each other. Alright, if you do the arithmetic, this becomes 23 over 3 minus negative 27, and then that comes out to 104 over 3. Okay, so that was the exact answer in decimal form. If you wanted to write this as a mixed numbers, this is equal to 34. 3 goes here 3 times. And then here 4, 12, remainder 2, 24 and 2/3. Okay, so this is the exact answer. You notice that the other answer we got, 34, is smaller than this, so that's consistent with our prediction that our result is an underestimate. Okay, now let's go ahead and do the second part of part C, where we have to find the percentage error. Okay, So that's basic math to do. So let's write down the formula first. Percentage error is basically the absolute value of the estimate minus the actual divided by the actual multiplied by 100. Okay? So let's go ahead and apply that here. So the percentage error of the trapezoidal approximation is the estimate, which was 34, the answer we got initially, minus the actual area is what you got when you did the actual computation of the definite integral, which is 34 n to third. That's divided by the actual, which is 34 n to third. And then we're going to multiply that by 100. Alright, so if we do this by hand, we'll have, see, this becomes, the numerator is 2/3, actually negative 2/3, over, if I write this as a mixed number, as an improper fraction like we had before, it will be 104 over 3. Absolute value of that times 100, which equals, you can write this as negative 2/3 times 3 over 104 times 100. If you plug this in your calculator and do the calculations, this is going to be approximately, well, let's use a decimalization here. It's going to be 0.19. I left out a zero. So let's do that again. It's 0.019. 0.0192 to 4 decimal places. We multiply that by 100. That's going to move the decimal place back twice. So it's going to be, our percentage error is approximately 1.92%, which is not that bad. So 1.92% is our approximate error in this situation. All right. So there you have it. And thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel so you can get updates to other cool clips such as this. And do post a comment to let me know what you think about this clip. I appreciate it. More clips can be found on mathgotserved.com/calculus. Thanks again for watching and have a wonderful day.